Now this is the time to go over data collection and data analysis in Internal Assessment Group for Science in IBDP. You remember this map and you know that in previous videos I already explained title and research question, re-explaining of research question, background information, hypothesis, and variables and methodology. Now this is the time to concentrate on data collection and analysis. Let's do it. In data collection and analysis, basically you will have two different distinguished parts, collection and analysis. First, raw data collection. Any quantitative observations recorded during the experiment should be mentioned. Give sufficient information about the gathered data. How did you collect data? And the second, show that you know how to take appropriate increments and enough trials to support your data. For example, you have increased the voltage by steps of 0.5 volt. Why? Give a reason for that. The second is raw data analysis, transforming and processing data. Actually, you will have tables and graphs. Another very important point is uncertainty. First, raw uncertainties. Talk about the raw uncertainties and how you have measured them. What do I mean by that? We have, again, two types of uncertainties. About the uncertainty in my measurement playlist, I have a complete explanation. Please watch the related videos. But anyway, I can shortly re-explain them here. Let's say you have used a digital ammeter, okay? A digital ammeter, and on this screen, you have already observed this data at 3.5 amp, 4.3 amp, and so forth. The last right figure is in the number place of tenths. So the uncertainty will be plus or minus 0.1 amp regarding the digital apparatus you have used. So here you will have a column for amp for the current, and here it's in amps, and here you will write plus or minus 0.1 amp, the uncertainty. The other is the raw uncertainty based on average. Let's say you have measured the current in 3 or 5 trials, whatever, and then you have taken average. So the reported values are like this. Here you will have current, the trial 1, the trial 2, the trial 3, and the average, okay? Here the trial 1, trial 2, trial 3, and the average, okay? Based on that, the uncertainty will be equal to maximum value among the 3 trials you have done minus minimum divided by 2. So row by row, it will be different. These are the two different types of uncertainties you have. The next is propagation of uncertainty. Sometimes you have processed value. For example, in physics, we have electrical power like VI, voltage times current, okay? And then for finding the absolute uncertainty here, first I used fractional uncertainty. It's delta P over P, which is equal to delta V over V plus delta I over I. Then you rearrange the equation like delta P equals P times delta V over V plus delta I over I. So row by row, the values are different for uncertainties. Let me show you a sample. Here I have the voltage. Here the raw uncertainty is plus or minus 0.1 volt according to the digital apparatus I've used. The current here based on trials, trial 1, trial 2, trial 3, and the average here. So here you will have uncertainty based on 3 trials. So it's different. You will use the range. Maximum value in this range minus minimum value in this range divided by 2. So row by row it will be different. Let me show you. This is the first row, and then the value, and then the uncertainty for the first row. The second row different. It's different from the first column. In the first column, you have the same uncertainty for all values, but here it differs. The last will be the processed quantity, like the power. So here, according to the propagation of uncertainties, as I explained, you will have your specific uncertainty for each value. Let's say it's like delta P equals P times delta V over V plus delta I over I. Please explain them in detail for the reader. They must see that you are aware of the uncertainties and how did you measure them, and watch the matching of the values. For example, in uncertainty, you know that the last right figure must be compatible with the reported values. Let's say let me show you here, the power is, I don't know, 4.2 watts, okay? The uncertainty cannot be 0.01 because the last right figure here in uncertainty is in number place of hundredths. So the values are reported maximum up to 0.1. I mean, a tenth of watts. So it's not compatible. So you should be aware of them. You can learn this lesson in my uncertainty video. Please watch that. When you report your graphs using a spreadsheet or any software you want, you must be aware of some necessary modules on that. There are some specific elements must be shown. For example, here we have a label for the graph. Put a label. Which type of graph is it? Is distance versus pressure. The other is the caption. Give a caption for that, and the caption must have address. You may refer back to this specific figure or graph, and so it must have an address. The distance pressure graph in the first trial, okay, rather than the distance pressure in general. Here is for the first trial, and also is the number, the specific address for this figure, 6.1. The other is the label of the axes and units. All axes must have a name, a label, pressure, distance, current, voltage, whatever, and unit. The other is error bar. You must show the error bars. If you have a specific error bars, show the error bars on your graph. And the other is the best fit line. Best fit line, we do not mean necessarily it's going to be a line. It's a general expression we use. It could be a curve. Show the best fit line. It's also very important. And the equation of the best fit line. It's very important. And the R square, which is called coefficient of determination. Coefficient of determination shows to what extent the selected best fit line is matched with data points. It's always a number between 0 and 1, and it's supposed to be very large, very close to 1, to show you have already selected the best of the best fit line. The idea and explanation of a curve fitting through the error bars will add a lot of weight to your analysis. You have used a manual method or a spreadsheet, a specific software, whatever, to select this best fit line. Tell the reader how did you do that. It will give a lot of weight to your analysis. It's very important. For example, you know that the best fit line must pass through all uncertainty zones. So you have done your best to pass it through all uncertainty zones, if it's possible, if you don't have any outliers. In linear graph, although I have already mentioned and explained it in my measurement playlist, as mentioned in graph analysis, but anyway, I re-explain it again here. In linear graph, if the arrangement of points demonstrate to have the possibility of having a line for the best fit line, you will select it judged by eyes or maybe using a software, and then the slope. It's very important. Pay attention in the linear case. I will concentrate on the first and the last data points. And then I make two rectangles. The vertical size of this rectangle is based on the vertical extension of the error bars, and the horizontal also likewise, the width. And then I concentrate on the corners. Here I concentrate on the bottom right corner, and here I will concentrate on the top left corner, and then connect them. It will give you the maximum slope. Then measure the maximum slope here. Then again you go over the other one, which is the connection between the top left corner and the bottom right corner in the last rectangle. And then you will find the minimum slope, okay? When you do that, you will find your slope. Your slope is going to be maximum slope plus minimum slope divided by 2, the average. And the uncertainty in a slope will be maximum slope minus minimum slope divided by 2, half of the range. It's very important, okay? So in linear graph, be very sensitive to this action and explain it in detail for the reader. In data analysis, avoid interpreting data. Interpretation of data is not going to be here. I will explain it in future. The other to be avoided is reasoning for why the graph or data is like this. But the data show something, I don't know, as a linear arrangement or linear best fit line, curvilinear, exponential, whatever. Do not try to explain it for the reader that why it is line or why it is not line. The trend of data, whatever you see, is not going to be explained or interpreted here. The next is extrapolating the graphs. Avoid it. Seriously avoid it. Do not extrapolate. You have a graph and you have covered a few points. Okay, do not extend your graph and then extrapolate it to infinity or a negative infinity. It is not a correct way. Do not go beyond your data. Just limit yourself in the measured data and the present values. Prediction for the data beyond what you measured. Do not predict something. You may have already found that, I don't know, the behavior is linear in this range. Do not predict that it will be linear forever. It is not the proper place to make that prediction, okay? So avoid these 4 items. Thank you for watching this video. It's done. In the next video, I will go over results and I will tell you how to make the interpretation over the analysis you have made. See you soon.